Right, so the photoelectric effect, and this is all about the idea, the concept that light is no longer travelling like a continuous wave. It's now travelling like a stream of particles, and those particles are called photons. Each photon is a tiny packet of energy, and it has an energy equal to h times f, which is Planck's constant times by the frequency. And that equation E equals hf is a really important one to know. You're given it, but you still need to really kind of understand it and be ready to use it in lots of different answers. So what we've got here is a charged metal plate. So this plate on the left hand side is negatively charged. It's been filled with electrons, and we're shining light onto it. At the moment it's light which has an intensity of 50%, so medium brightness, and it is very red, almost in the infrared region. Now infrared, red light is, well, from the visible spectrum, red light has the highest wavelength, and that means the lowest frequency. And if we use the equation E equals h times f, that means each red light photon is carrying the lowest amount of energy. So a red photon, well, thousands and thousands, millions of red photons are travelling across this space, and they're hitting the electrons in this metal plate. Now each one of those electrons has an amount of energy which it needs to receive to free itself from that metal plate. So there are very weak forces tying those electrons into that metal plate. Those electrons are free, they're delocalized electrons, so we're not trying to ionize the metal or anything like that. It doesn't take much energy to release them, but there is an amount of energy required, and that energy is called the work function. So the work function is the minimum amount of energy we need to give to each electron to free it from the metal. If we give the electron that amount of energy, the electron is then freed and it can move. If it has energy more than the work function, so if it's given energy which is greater than the work function, it will use the work function portion of that to free itself, and any energy it's got left after that it will use as kinetic energy and go flying across this gap. So if we decrease the wavelength, which is the same thing as turning up the frequency, we should start to see electrons be emitted. So we're in yellow light, into the green, and there we go, we've got the first few electrons being emitted. So now we know that each individual photon, which is a packet of energy, equals hf, has enough energy to release the electrons. So the energy of each individual photon, so hf, must be at least equal to the work function. And in fact we know it must be a little bit more than the work function, because those electrons are moving with the kinetic energy. If we then keep on increasing the frequency, which is the same as decreasing the wavelength, those electrons are moving faster. They have more kinetic energy. And there's another equation here. So the energy of the photon, hf, is equal to the work function of the electron plus whatever kinetic energy that electron now has. If we turn up the intensity, the brightness of the light, then that doesn't make the electrons move any faster, but it means we get more electrons moving because there are more photons striking the electrons in the first place. If we turn the intensity right down, the electrons stop altogether, and a low intensity means a few electrons still moving at that same speed. With the photoelectric effect, the interactions are what we call one-to-one interactions. So it's one photon striking one electron. If that single photon has enough energy to free the electron, then the electron will go. If the photon doesn't have enough energy, then the electron won't do anything, it will stay exactly where it is. So if we go back to kind of the violet lights and turn the intensity right back up. This was one of the big bits of evidence that led to the whole beginnings of quantum physics. And this couldn't be explained using the idea of light travelling as a wave, because if light was a wave, we should be able to turn the frequency right down, work in red light, and just have the intensity bright enough so that the energy builds up over time to cause the electrons to be released. However, that doesn't happen with red light. It doesn't matter how high that intensity is, no electrons are going to be released. So with 100% intensity with red light, no electrons. if we turn the intensity down to 5% but use ultraviolet, we get electrons. So all that matters is the frequency of the light, and that's what led people like Einstein to come up with those equations: E equals hf, and then hf equals work function plus maximum kinetic energy. One extra little bit of terminology here. When the photon has an energy equal to the work function of the electrons, then we say the frequency of that photon. So we'd have the equation hf, the photon energy, equals the work function. When that happens with no kinetic energy, then f we would call the threshold frequency. That's the minimum frequency required from a photon to cause an electron to be freed.